Welcome everyone. This is the talk on Imagery and Raster Analysis on the web using ArcGIS API for Python. I am Atma Mani, and joining me today is Chunming Peng and Navajesh Noman. In this talk, we will introduce you to WebGIS architecture and what is required to perform raster analysis. Then we will talk about the Python API and the layout of the raster module. We'll give you a quick look into a hello world example. Then I will hand it off to Noman to talk about raster analysis concepts. Finally, we will each show you a few demos covering imagery analysis and raster analysis, and then we will conclude. So let us talk about imagery and raster analysis on the web. To perform this analysis on the web, you need ArcGIS Enterprise. The Enterprise is a collection of a few different applications working in synchrony, such as the web adapter, a portal for ArcGIS, an ArcGIS server, and possibly a data store for all the GIS data. If we expand the server, there are a few different kinds of server roles, such as the hosting server, image server, geoanalytics server, notebook server, to name a few. For this talk, we need ArcGIS Image server federated to your enterprise. In terms of client applications, the enterprise supports multiple kinds of clients, including full-fledged applications like ArcGIS Pro, web-based apps like MapViewer, or user-built custom web apps. You can also perform imagery analysis through APIs, such as the REST API and the ArcGIS API for Python. And as you guessed, this talk is going to be about making use of the ArcGIS API for Python for performing imagery and raster analysis against your WebGIS. So let us take a look at the Python API. This is a relatively newer API or library from Esri, but it has grown quickly. With more than 2,300 functions and methods, this library can be used to perform a wide variety of tasks, including WebGIS administration, such as creating and managing users, managing the security models around this, managing the servers, the federation aspects, machines, services, licenses, etc. You can manage your WebGIS content, including publishing new content, cloning content from one organization to another, updating and keeping these items periodically up to date, setting up distributed collaborations between different GISs, and creating or managing content for other applications like workforce, story maps, survey 123, etc. You can perform sophisticated modeling or spatial modeling using a number of spatial analysis tools. You can read your data into spatially enabled Python data frames and make it available to third-party Python libraries. You can perform imagery analysis, including managing your GIS data or imagery data, performing information extraction out of these imagery or raster products, and also working with specialized photogrammetric products to build outputs such as orthomosaics, surface models like digital elevation models, etc. You can perform suitability analysis or location analytics. You can perform drive time analysis using network module. You can also perform geocoding analysis. A recent addition to the Python API is the ability to perform spatial machine learning. The arcgis.learn module, but in particular, allows you to build deep learning models to help you with tasks such as detecting objects in satellite images, classifying pixels, classifying objects, performing instance segmentation, working with text data using natural language processing, etc. Finally, you can also build information products. You can visualize your data on Jupyter Notebook using interactive mapping widgets. And as I mentioned earlier, you can produce information products like web maps, web scenes, or publishing of WebGIS layers. This talk is going to focus on imagery analysis and everything about it as we have highlighted in orange in this slide. So let us take a deeper look at the raster module of the Python API. An important class in the raster module is the imagery layer object. It represents the image service published on the web, and it has properties to inspect various details of the data that you're working with, and it has methods to query, filter, and dice the data. A bunch of manager classes help you to perform content management on your imagery datasets. A newer addition to the raster module in Python API at version 1.8 is a raster class. Raster objects here can work with both web-based imagery layers as well as local raster files. Thus, it provides you a unified API irrespective of where your data is stored. Then, shown here in purple are submodules within the raster module. These submodules each contain numerous functions that allow you to model the problem you're trying to solve and compute on it. You can perform both on-the-fly computation for visualization as well as distributed computation for persistent data products. So in this talk, we will focus on the imagery layer and analytical functions from these submodules. Now, let's take a quick look at a Hello World example to see the Python API in action. The first thing that we do with the Python API is to import the GIS module. Now I make a connection to ArcGIS Online as an anonymous user. Then we can search ArcGIS Online for imagery layers. We do that by using the search method and passing out item type as imagery layer. And here I'm only asking the server to give me 4 different items, and I'm displaying the results of those the search results. Everything that you see here, each of these entry is called an item or an item object. If you want to get specific results, you can specify a particular search term in the query field. And so in this case, we are going to search for Landsat 8 images or Landsat imagery layers corresponding to Landsat 8 sensor. I'm getting up about 7 different items to show here. So we can see various different types of Landsat layers published by different users like Esri in this case, shown as different items. We can drill deeper into this and filter out just the Landsat 8 views item for the rest of this workflow that we are looking at. The data type or the type of the object that we are working with so far is an item object. This item object is going to have a property called layers, which will give you back an appropriate layer object. If the item corresponds to an imagery layer, you get an imagery layer object. If the item here corresponds to, say, a feature collection, a feature service collection, or a feature service, you get back a bunch of feature layer objects. Now we will store this imagery layer in a variable called Landsat layer. And as you can see, it is of type imagery layer. You can quickly preview an imagery layer in a Jupyter notebook just by calling that variable and running it. You get a quick export of the extent and the data that is contained in that imagery layer. If you want to, this is just an image, but if you want to view this on an interactive map, you can do that as well. Here I'm creating a map widget, and I'm adding that imagery layer into this map widget. So once this loads, you can start to zoom in and pan and start looking at different extents. So for instance, let's try zooming into Southern California and see the data that is stored here. Now, earlier from the slide deck, we have seen that this imagery layer object has a bunch of properties and methods. So let us take a look at what those are. Here in this cell, I am trying to print only those public properties and methods, and you can see there are a bunch of them. So the rest of the notebook, we are going to pick some key properties out of these and use them to inspect and get more details about what kind of data we have within this Landsat layer. The first information that we'll try to extract is spectral resolution. So in general, imaging sensors on all these remote sensing platforms like Landsat platform, they collect reflected energy in multiple wavelengths, and we call them as bands. So Landsat 8 sensor has 2 instruments. One is a optical land imager instrument, which collects data in 9 different bands. And then there is a thermal infrared sensor, which collects data in 2 bands. The graphic here shows you the different bands for Landsat 7 and 8 satellites, as well as Sentinel-2 satellites. All of these boxes correspond to different bands in each of these satellite sensors. The gray area that you see here corresponds to something called as atmospheric windows across different regions or different wavelengths of the electromagnetic spectrum. Atmospheric windows are regions where the reflected energy from the surface of the Earth can reach the satellite sensor without much of re-radiation or absorption or scattering effects. So that's why you would see that a lot of these sensors are placed well within the atmospheric windows. Now let's see what properties we can use on the imagery layer to get information about what kind of wavelengths and bands that we have on the imagery data. One property to use is the band count property, and we can see that there are over 11 different bands in the Landsat layer that we have right now. Next, we want to drill deeper and find out what are the different wavelengths these bands comprise. So for that, we are going to use the key properties, and it gives you back a dictionary, and we are going to extract the band properties out of that particular dictionary. I'm putting that into a data frame so we can easily see that as a table in our Jupyter notebook. Here we go. We have 8 different bands shown here, and we have different wavelength minimum and maximum. We call this the bounds of the particular band. And each of these bands also have a useful name that you can use to refer to them. To talk about a different kind of a sensor, I'm going to connect to my ArcGIS Enterprise. And here I'm going to search for a data set from a sensor called ARcGIS. This ARcGIS is a hyperspectral sensor, and which stands for Airborne Visible and Infrared Imaging Spectrometer. If you look at the band count, you will notice that there are 224 different bands. Just think about it. So many different bands in which optical and imagery data is being collected. If you look at the wavelengths, here I'm plotting the first 5 wavelengths. It starts from regular blue channels from 430 nanometers, and it goes all the way up to 2400, well into the mid-infrared range. This is a really rich kind of a data set. Now, we looked at a few different properties, and using them, we explored a particular key metric in imagery or remote sensing data, which is spectral resolution. Next, we'll jump on to a different kind of a metric called spatial resolution. In simple terms, spatial resolution is a measure of the finest detail that can be distinguished or made out in a raster. It can also be thought of as the area on the ground that a particular cell will cover, and so it is also called as the ground sample distance. So if you have the smaller the area that a particular cell covers on the ground, the better is the resolving power of the imagery or the satellite sensor, and so it is said to have a better spatial resolution. So in the graphic here, you can see that it's the same particular car that we are viewing using 3 different spatial resolutions. The one on the left has finer spatial resolution, so it is easy to make out different aspects of the car, including the front, the back, and things like that. As we get coarser spatial resolutions, it is much harder to make out what exactly the particular object is. So for instance, if you take a sensor like WorldView 2, it has a very high spatial resolution of 0.46 meters, which is approximately a little larger than 1 foot. When you compare that with Landsat 8 sensor, the optical land imager camera on Landsat 8 has a spatial resolution of 30 meters or a little less than 100 feet, so which is much coarser. But if you look at other wavelengths, like you get even coarser spatial resolution of 100 meters, and thermal infrared bands have 10 meter. Thermal infrared has a 100 meter spatial resolution, and panchromatic bands have 10 meter spatial resolutions. Let's see what kind of properties we can use on the imagery layer to get this kind of spatial resolution related information. You can use the pixel size X and pixel size Y, and if you query it, you get the values as 29 point decimal, 30. What exactly does this actually mean? To understand what these numbers mean, you need to understand that these are given in the units with which the imagery layer is projected or published with. To get what is the spatial reference of the imagery layer, you can use a spatial reference property. You get back a dictionary with WKID and latest WKID. The latest WKID of 3857, I know that it corresponds to WebMercator. WebMercator is a projection system, and the units for that projection system is meters. So with that information, we know that the pixel size X and Y of the Landsat sensor has all been resampled to 30 by 30 meters. The one thing to note here is that the satellite itself may collect data in a particular resolution, but the imagery provider may resample, may perhaps upsample or downsample that particular data set into a particular resolution before giving off to customers. So data from a satellite usually goes through a long pipeline of various different corrections to fix for geometric distortions, radiometric distortions, atmospheric influence before it gets to the hands of the end user. So during this process, the spatial resolution may get distorted a little bit. So that's something to keep in mind. So we saw what properties we can be used to query spatial resolution. So earlier we saw spectral, then we saw spatial. Now we'll move on to a different kind of a metric called radiometric resolution. Radiometric resolution is the ability of a sensor to detect subtle differences in energy levels for each of the wavelengths. We can also think of it as what levels of brightness can the satellite sensor make out. So if you have a higher radiometric resolution, the sensor is able to make out very fine and subtle differences in the reflected energy or emitted energy. If a sensor has 8 bits to store data, then we can say it can represent 2 raised to the power of 8 equals 256 shades of gray in a particular band. So we call this the radiometric resolution of that sensor is 8 bits. Sometimes newer and more advanced sensors have a radiometric resolution of 2 raised to the power of 16. Usually the traditional cameras on our cell phones have 8 bits to store data or 256 shades of gray for each of the 3 bands, red, green, and blue. So what property can you use on the imagery layer to query this kind of data? You can use the pixel type property. When I query that on the Landsat layer, my result is S16, which stands for signed integer of 16-bit depth, or 2 to the power of 16 is the radiometric resolution of this particular data that we have. I have a different data set that responds to the digital elevation model of the Arctic, and the pixel type for that is F32. I'm just showing this for example, which means that the F32 stands for floating point 32, which is way higher resolution compared to what we have in for the satellite Landsat data. After radiometric resolution, let's talk about temporal resolution. This is the fourth and also an important metric when it comes to collecting satellite imagery data. Temporal resolution is the periodicity with which a particular sensor images a particular location on the Earth. So let me play this video and talk to it. You can also think of it as a revisit cycle or repeat cycle. So the repeat cycle is determined by many different factors. Things like the orbital height with which the satellite is flying above the surface of the Earth, the inclination with respect to the poles, the width or the field of view that can be viewed by the satellite sensor in a particular image. So if you have wider field of view, then you can cover larger parts of the Earth in each of the individual scans. And this radiometric or periodicity will also depend on the latitude. So the higher in latitude that you go, usually the periodicity is much closer compared to on the equator. By tradition, we generally quote the periodicity or the temporal resolution at the equator level. So Landsat 8 sensor has a temporal resolution of 16 days revisit. The Sentinel-1 mission has 2 satellites, so it has a much finer resolution of 6 days. By now, it is very common to have multiple satellites working in synchrony with one another, and sometimes these are called as satellite constellations. Let's take a look at what kind of properties we can use to query the temporal resolution of the dataset that we have. I'm drilling deeper into a particular property of the Landsat imagery layer. Now of this, I'm trying to look at a particular property called fields I'm going to print out all the different field names that I can use to query this imagery layer. At this point, I want to tell you that the imagery layer for the Landsat that we are looking at so far, let me scroll back to my map. This imagery layer is not a single mosaic of one large image, but instead it is hundreds or maybe even thousands of Landsat scenes that are all put together into an imagery layer. It is more like a collection of various different Landsat image scenes that were captured at different points in time. That's the reason why you see all the speckled nature of these individual boxes. These individual boxes are different Landsat scenes that are collected data for this region in different time periods. With that in mind, what we can do is you can query the imagery layer, giving it certain search conditions, and try to find out all those scenes that fall within a particular area of interest. So to do that, I'm going to use a geocoding module and geocode an address. I'm going to choose Redlands, California, which happens to be the location for Esri headquarters. And I can get the extent for that particular for that particular area. What's important here is that I need to match the spatial reference. So this geocode function will accept my using the out_sr parameter. I can pass it a particular spatial reference in which I want the extent to be collected, and I choose a spatial reference of the Landsat layer so things will match. So once I have this extent, I can use the geometry module of the Python API to create a geometry filter using the overlaps function. So what I get out of this is a filter that will refine only those Landsat scenes that fall within or that will overlap with the extent of the city of Redlands. So next I'm going to use the filter by method off of the imagery layer, which is the Landsat layer, and pass a where clause. I'm going to give it a category type, and I'm going to specify the cloud cover should be less than at least 10%. And the geometry is corresponding to this Redlands geometry that we just defined earlier. So let's run this. What we get back is a filter by operation on the imagery layer. Next, I can run the query function off of my filtering result, and I get back a feature set object. So I can verify that by calling the type on the query result, and I got back a feature set. This feature set contains 51 features. What that means is there are 51 Landsat scenes that fall within this particular geometry filter and also match this particular query filter that there should be less than 10% cloud cover and should be of category 1. I can quickly take a look at the results as a table. I'm only previewing the first 5 of that 51 records that matched. Now you can see the name of each of these Landsat scenes and various other characteristics like the date and time it was taken, the sensor name, and things like that. Now I can also turn this result, the data frame that we have, into a spatially enabled data frame and put it on a map, and that's exactly what I have here. What we see here in yellow are different boxes that correspond to the footprints of the different scenes of the Redlands Landsat area. So if we zoom into the border of this and get really close, you can see that there are various different scenes that are all stacked up together, covering this particular area of interest. If I'm interested to know what are the different time periods in which we have this data, in one way or the other, we can say for Landsat 8 scene, Landsat 8 dataset in this particular imagery layer, and for the region of Redlands, what is my temporal resolution? I can answer that using this line of code. I'm picking the acquisition date column and sorting by date time in ascending. And I can see that we have data all the way from 2013 April 20 until 2020 January 18. This is fairly recent data considering that I'm recording this in March. So this was a quick tour of using the Python API, in particular the imagery layer object of the raster module to connect to and to, to inspect an imagery layer object and get all the different um, criteria such as different types of resolutions and also quickly previewing that on a map widget. Next, we are going to look at some technical concepts to understand for performing raster analysis. And for that, I'm going to hand it off to Noman.
Now that you know about the ArcGIS API and the modules, let me talk about raster analysis. ArcGIS have 5 core capabilities for imagery. The first one is, of course, content. You want to first bring content so that you can actually do whatever you want to do with it. Now, ArcGIS have support for all major sensor types, including Sentinel, Landsat, and has support for specialized sensors like microwave, weather, etc. So you can actually bring in your data the way it's supposed to be with all the necessary information, and you can interpret the data in a correct manner and work with it. Now that you have content, what are you going to do with it? Of course, you want to visualize it, right? So in ArcGIS, we have many different tools to help you visualizing it the way you want. We have different symbology, we have other appearance correction method, stuff like that. But it's not just the way you want to visualize it. You may want to dig deep and actually find more about your data. To do that, we have tools for probing like temporal profile and summary statistics, other tool that actually give you more insight about your data. We also have charting tools so that you can actually create your own chart and take a look at it closely. Well, after that, you want to analyze your data, because with that you will create more new information and gain insight. We'll talk about analysis in great detail in a minute. Once you do all this thing, the way you want to disseminate this information to everybody is maps, through map. Everybody understand map, you can connect to it, you see it all the time. So we have capabilities to create different kind of maps in a very rich environment so that you can communicate your data and the information that you want to communicate through map production. You also automate the process so that it can happen in a efficient manner. You also have vast capabilities to manage your data and disseminate it, because you not only want to keep your data locked in your own computer, you want to open it up to the broader community. And the way you do that by creating services, and you serve the data to broader community. So as you can see, ArcGIS platform has all the necessary capability that you need to work with raster. Now let's look at the analytical capabilities in broader categories. Of course, when you capture an image, it is not always correct, right? You have problem with the shape of the earth, which is curved, that makes it harder to create a flat image, right? Or capture a flat image and then look at it and understand where is what. Of course, the atmosphere itself causes additional challenges because sensor cannot look through it. So we have to make some correction for that. The seasonal variation or day-to-day variation actually change how much solar radiation you're getting, and that also affect what you are looking at from miles up in the atmosphere. Imperfection in scanning instrument is natural because we are creating instrument and no instrument is perfect, right? So you have all these different ways that the imperfection could happen to your captured image, and we have ability to correct them through geometric and other radiometric correction. Once you correct it, still you may not like the way it's looking. Either it's too dark, too light, so you can of course change the brightness, contrast and stuff like that. Oh, some area might be blurry, right? Like, taking pictures, your hand shook, right? So what do you do with those kind of images? You can actually use filters and other functions, convolution functions, to actually make those correction. You can detect edge, you can actually blur an image if you want, right? Or you can go either way. So there are many options, there are many possibilities that you can do. One of my favorite one is actually pen sharpening function. Why is that? Because it takes a high resolution panchromatic image in black and white and look at another colored image which is lower resolution multiband spectral image, and now fuse them together to create a multiband high resolution image. If you see, on the left it is a multiband low resolution image, on the right it's a panchromatic high resolution image, and once you actually do pen sharpening, look at the beautiful high resolution image you get at the bottom. Isn't it beautiful? We have other capabilities in image processing, of course. You can do band math and create indices. One of the most common one is NDVI. What does it do? It actually tells you about what you're looking at and how green it is. So of course the high value represent forest areas, large vegetation and stuff like that, and the moderate value represent area of shrubs and grassland. Very low value, of course, where there are very little or no vegetation, like urban area, rock, concrete, bare soils, stuff like that. Extremely low value, on the other hand, represent cloud, water, snow, no vegetation at all. Now you have all this information, but you want to take a look at it in a nice way so that it becomes obvious. An NDVI colorize function actually let you do that. It combined two things. It combined the NDVI function and actually apply a color map on top of it to display the result. And as you can see on the top, you have the NDVI value in green, but when you actually do the colorize, you get a very nice vivid picture of what is going on. There are more other capabilities in image processing, and one of the most important one, which is very commonly used, is image segmentation and classification. What does it do? It lets you look at an image and tells you what is what, right? You can differentiate between a cropland and urban area or water, right? Or it can let you differentiate between a car versus a plane, right? So we have rich functionality to do this kind of image segmentation and classification, whether you want to do an object-based classification or pixel-based classification using variety of technique that we have, supervised and unsupervised. Oh, we have lots of machine learning technique too. Now that you have done image processing, let's go back and talk about some of the basic raster analytical capability that you have in GIS. Distance analysis is a very common one that most of you do. And distance analysis, what does it do? It creates the map of distance, whether it could be at the shortest distance, Euclidean distance, straight line distance we call it. Sometimes you can find distance along the slope. You can also do cos distance. Why you do all this thing? Because you want to find the shortest path between two locations, or sometimes you want to find the optimal path between multiple locations. Suitability modeling is the most commonly used analysis that people do with raster. What does it do? It finds the area that is suitable for certain kind of operation. Let it be building a school or your cell tower or the new Starbucks location. It considers multiple factors that affect the suitability. For example, it combines categorical data like land use, soil type, and other continuous data like slope or property values, aspect. Depending on your problem, you may look at different kind of variables to combine together to create a suitability map. And once you have that, what you do, you use locate region to find the best location that meet all your criteria, the size and shape and everything, to find the best location for your work. Hydrologic analysis is all about water on your landscape. It let you derive the flow pattern from a DEM and create watershed or stream network, flow distance, and other hydrological characteristics. These are all important to understand your landscape or to create mathematical model. That information goes into that model and it does simulation and bring it back. You can actually do other modeling in GIS too, like flood inundation model, erosion models, and stuff like that. There are many other areas you can also perform raster analysis. Interpolation and density, an area where actually you get your observed data and then create either continuous surface or you actually predict the value like a density and stuff like that. Now, elevation, rainfall, and chemical concentration, all these things are a good example of showing creating continuous surface. You can also find density of crime, road accident, and assets, stuff like that. And all those are important information to do different kind of analysis and application. Derivation of land surface characteristics is something very common thing that we do and without even thinking too much about it, like creating hillshade or slope or aspect. Curvature of your land surface give much more insight about your land surface. Solar isolation, visibility. Visibility is one of the most common one used for many reasons, right? Even so, establishing a cell tower sometimes use visibility, or you want to actually create a landmark and you want to make sure that everybody can see it, or you want to create your wind farm and you want to make sure that not everybody can see it from all the area. Depends on your purpose, you can go one way or the other. Statistical analysis is something that we do on a regular basis, on a cell by cell basis or neighborhood basis or a zone basis, and all this information is actually used as an independent information or sometimes used in another application. Now, all this analysis is as good as your data, and most of the time the data is not perfect. So what do? You actually take your data and clean them up, and we have many tools to do that. Generalizations are kind of the general term for some of those tools, where it actually take your data and get rid of unnecessary information, or it actually correct your data so that your analysis result is better, right? And map algebra is a way of performing this analysis, and you can actually string all your tools or function and operator together to perform a very powerful analysis. Now that you have learned about all the different kind of analysis, let's take a step back and group them into a couple of broad categories so that you understand these tools better. Now, one of the basic fundamental category is local and focal operation, where you are looking at a cell level and looking at one cell in one raster and the corresponding cell in another raster or image and doing some operation. That is called a local operation. It's a cell by cell operation. Focal operation, on the other hand, when you are looking at a cell and also looking at your neighboring cell, right? What is above me, below me, on the side, on the left, on the right. That's your focal operation. And to make a decision or to analyze something, you are looking into all of them together. right? That's a focal operation. Custom Python raster function, we'll talk about that later, fall into that category, and most of the raster function fall into that category too. Zonal analysis, on the other hand, where you are looking at the entire zone collectively. Now that zone could be in one area, or it could actually distribute it in other area, so it could be sparse. It doesn't have to be contiguous. And those operations are called zonal analysis operation. Global operation, on the other hand, is actually something where you need to look at probably your entire data set so that you can compute something. Hydrologic analysis or cost distance is a good example of that, because in order to find out how much water is coming at the outlet, you have to look at your entire landscape. So that's an example of global operation. Similarly, to find out the best path over a landscape or a terrain, you have to actually look at every alternate path. And then you can find it, which is also another example of global operation, right? Now in ArcGIS Enterprise, we want to distribute this operation. You want to compute it faster by distributing it. So we call it distributed computation. And it is not easy when you talk about the global analysis, but it is relatively easy when you are doing local and focal operation. So as you can see, the difficulty actually varies, and for local and focal it's much simpler or relatively simpler. And as you move down in this kind of different level of operation, zonal become a little harder, and then global become really harder. So as you can see, the intensity of color on your arrow pointing downwards tells you how hard it gets when it goes to global, right? Now that you know about different kind of analysis, let's introduce something very exciting and important analytical technique that we used in ArcGIS. But before I actually talk about what we refer as raster function, let me give you an example which you are all familiar with. You have your phone, you take a picture, right? And once you have a picture, you look at it and say, how can I make it more exciting? You go through the filter and you apply it, right? As you apply different filter, the picture immediately change and show you what it may look like with that particular filter. And once you are happy, you accept it. Now, what is really happening when you are applying this filter is actually changing the picture on the fly without really changing the actual picture, the original one, right? So raster function works exactly like that. It performs operation on the fly. Now let's take another close look. What actually it does? It gets some cell from an image in a specified area, whatever area you are looking at, not the entire area, a small area of interest that you are looking at. It gets the pixel value at a resolution that you are looking at, and apply raster function to it, and you can see the new information coming out of it. You can look at that information on your desktop, tablet, or your browser, whatever you are looking at, right? You can also apply a function chain which will work together to produce the new information. You can also cache and look at a new image and stuff like that. So let's take now an in-depth view of raster function. What is it? It is an on-the-fly processing tool, as you can say, or let's call it raster function, right? Raster function is not permanently applied to a data set. You can save the output as a permanent, but raster function itself does not make it permanent. Rather, it actually do the processing on the fly. As you are looking at the image, it actually access that area that you are looking at and do the kind of the analysis on the fly. As you move, it look into the other area and then do the analysis on the fly. So it's very dynamic in that nature and very powerful too. there are many analytical functions available in out of the box, right? What you can do, you can chain them together to solve a complex problem or create new information. You can save it as a raster function template, and then you can take that template and apply it to an imagery, or you can actually embed with your mosaic data set and you can share it as an image service. So your image service actually, the same service can actually give you different kind of information depending on the template that is applied to it, right? This is also a great way to extend your analytical capability, and you can actually create a Python raster function and embed that in your chain to make it even more exciting and the out of the new analysis that is not available out of the box. And we'll talk about that in a second. Now, what are the different tools we have? We talk about all different kind of applications of the tools or category of tools, depending on the type of problem we can solve, or we talk about, the way the tool operates at a local, zonal, or focal, or global level. When you look at the entire set, you will find that it actually fall into different category, and in different category we have different kind of tools. We can do multi-band math, we can do different kind of band math indices, different kind of statistics, visualization and appearance, a category by itself where you can do many things. Data management is a long list. We have many things to do there. But then we also have many analytical capability that fall into interpolation, surface generation, and image classification segmentation, overlay, statistics, distance, density, hydrology. You can see there is a long list of two functions that are available in ArcGIS Enterprise that you can actually use to do raster processing. And when nothing works, of course, you can fall back to your custom algorithm to extend analytical capability. And that brings up Python raster function. Python raster function is a great way to extend analytical capability, right? It turns from raster to a new information. It is a Python script that defines that custom raster function, and it is not part of your original ArcPy. It allows ArcGIS to utilize custom raster analysis through a Python adapter, right? And it is supported on server and desktop. So if you look at the architecture, what happens is you have this your module, and it is loaded by this adapter, and then it presents itself as a raster function, which you can put it in a chain and do that. Now you have done all this analysis. Where does it go? You persist it, right? Otherwise, people cannot see it. You cannot use it later. How do you persist it? You can save it as a service, but while you are saving your output as a service, it does two things. It actually first save as a raster dataset using a format called cloud raster format, or CRF, and then publish it as an image service. So let's take a close look at this cloud raster format. What is it? It is the default output imagery format for raster analysis task. Whatever you're creating and saving, it actually use CRF to do that and publish it. It gets published as a hosted image service, and it is displayed using the rendering service, raster rendering service. It supports cloud storage and other file system, right? It is actually a raster dataset which is tiled with a predefined tiling scheme to make it much easier to parallel read and write. It also have local caching. It also optimized for your fat web client, and it has been extended to support multi-dimensional raster for first slicing operation or probing or profiling. Now that you know all about raster analysis capability in ArcGIS Enterprise, I need to actually refer to my colleague Chunming, who will show you all these capabilities in action. Chunming?
Thanks, Norman, for the introduction on raster analysis. Let us now dive into a demonstration about image classification. Aiming to extract features from imagery based on objects. Image classification is a type of supervised machine learning that classifies each pixel into a class in the training data. Now we are going to demo how this technique can be used with ArcGIS API for Python. In this example, we are going to perform a land cover classification using a Landsat image in Iowa and hand-labeled training data that we have classified 4 classes in total: the developed area, the water, the forests, and the cultivated or planted areas. We also published and shared the training samples on our enterprise organization. For the imagery layer, we are using the multispectral Landsat imagery layer hosted by Esri Living Atlas. We are not using the full global extent, but to set the analysis extent to a small region in Iowa. Also, we are performing a filter by to retrieve only one Landsat scene by object ID. Now we have the Landsat layer and the training samples ready. We are good to train a model. In using train classifier method, we first pass along the 2 input parameters for raster and training samples, and then we specify the classifier parameters. For example, we specify the method to be support vector machine model because it allows for complex data transformations and resulting boundary planes. Also, we set the maximum number of sample classes to be 500. Executing this train classifier operation, we are then returned a dictionary object, which contains the definition for the trained classifiers. If we look at the classes property of this dictionary object, we are going to see 4 classes, which corresponds to what we have hand-labeled previously. Now we have the model, we are good to apply the model on a Landsat image and make predictions. We are using classify method here and pass along the input raster again, and then the definition we have obtained from the previous step. Executing the classify operation would then return an analysis image service in which all the pixels are classified with one land cover type. Let's visualize the predictions. Creating a map view centering an Iowa, we first add the original Landsat imagery layer. And then we add the predictions. Look at the 4 types: the developed areas, the cultivated areas, the forests, and the water bodies. We will say the prediction is looking quite reasonable, and also the boundary lines are quite aligned. This is just how simple the image classification workflow is. Let's switch to ortho mapping, a module in ArcGIS API for Python to handle geometric distortions in remote sensing images. It is a combined process of ortho rectification and mapping. While ortho rectification refers to the removal of geometric distortion, mapping refers to edge matching, seam-line generation, and color balancing in order to produce an orthomosaic dataset. Looking at the workflow chart, the ortho rectification process consists of performing block adjustment, assessing accuracy, managing control points, and then refining the block adjustment result. This process is iterative. Before we move along with the workflow, let's make sure we have met the requirements. The first requirement is for the versions of ArcGIS Enterprise and ArcGIS API for Python. The second requirement is for Raster Analysis Server and the image server licenses. It is recommended that we make sure the ortho mapping and raster analytics are supported in the enterprise before we even start with ortho mapping, which consists of 4 steps. Due to time limitation, we are not able to cover everything here. Let's assume we have the image collection item already created. You can see the distortion and discontinuity between sub-images. Ortho rectification now comes into place. Compute sensor model is to compute the bundle block adjustment. To start with, we can perform this operation at the reduced image resolution using a quick mode. Look at how the image gets improved even after the initial block adjustment. Generate report is a method to create the quality information summary in an online PDF file. Also, you can manage your ground control points via 4 functions. You can do compute control points, match control points, edit control points, and query control points. After adding the ground control points, it is important to rerun the compute sensor model as to refine the block adjustment result. This time, adjust the image at a 1:1 source imagery resolution and setting the mode as refine. Again, we create a quality information report, and we can compare it with the previous generated PDF. Look at the mean reprojection error and see how it gets decreased significantly. Besides quality information, we can also visually compare 2 images. Here on the left, the image after initial block adjustment. On the right, the image after the refined block adjustment. Ortho mapping also provides methods to improve visual display. For example, compute seam lines and color correction is here to help cross-strip images that are collected on different days with different atmospheric conditions. When you are satisfied with the result of ortho rectification, you can then move on to the mapping process. Generate ortho mosaic method is to help create an ortho rectified imagery layer. Look how the seam lines are regenerated and how the color gets corrected. Another common application is to generate digital elevation models. The generate DM method is going to help create digital terrain model when you set the surface type as DTM, in case you are only interested in ground elevation. And it is creating digital surface model when you set surface type as DSM, when you also want to consider what's on the surface, for example, the ground, the canopies, etc. There's a lot more in our ortho mapping module, yet we are running out of time. If you are interested in the topic, please check out the developer's website for more information on ortho mapping. Now back to you, Atma.
Thank you, Chunming. Up until now, we have seen a couple of different applications of using imagery datasets from satellite images as well as from drone images, and using the Python API to extract information products out of them. Now let us look at other kinds of raster, non-imagery raster data and how to work with them. So in this example, we are going to look at elevation and derived products based on that. This is a case study where we are going to use raster analytics to produce a suitability model using weighted linear combination technique. We are going to try to identify places that have higher risk or susceptibility to avalanches. Every year in the United States, about 25 to 30 people die in avalanches. And a study was conducted around the ski resorts of Lake Tahoe in Northern California, and this study walks us through that. We know that a lot of different parameters, such as elevation, the aspect, the slope of the slope, amount of snowfall, the land use, land cover, all contribute to avalanches in different extents. And we are trying to build a model that will help us represent these different risk factors. And we're going to identify the places that have higher suitability or a higher risk of having avalanches. First up, we are going to import the Python API. We're going to import raster and a few different operators from the raster functions module. We connect to our enterprise. Then we search for a digital elevation model for our for our area of interest. Then we collect the land use land cover dataset for our area of interest, which is Lake Tahoe, and then a polygon layer with which we will clip the other rasters so everything will fall within a particular study area. First up, we are going to clip the digital elevation model, and we are going to look at it on the map here. Places with higher elevation appear with brighter shades, and places with lower elevation appear as darker. This is the actual lake itself, and you see that it's uniform and it is having the same elevation. It's a pretty large lake here. From past studies and literature review, we know that avalanches occur between an elevation of 2,700 meters to 6,000 meters. When we look at the legend of our map, we see that the study area spans from 628 meters to 3,200 meters. So what we do next is we try to reclassify this elevation data into 5 different zones of suitability. So the range that exactly falls between 2,700 to 6,000 is given the highest risk factor, which will be number 5, and other regions are given lower risk factors. So we use a remap function to perform that. After that, we will apply a color map on the result of the remap. So it is easier for us to look at in the map, and we can distinguish these areas in a much pronounced manner. So when we look at the colorized elevation data, we see that there are 5 different classes. Each class has its own color. The ones with red color are areas that are identified to have higher risk of avalanches just from an elevation perspective. We need to look at all the other perspectives and all put together and combine them based on their relative importance. But this is the first step. The next step is to produce a slope raster. Once again, from literature review, we know that most avalanches occur between a slope of 28 to 45 degrees. If it is lower than about 25 degrees, it's not steep enough to cause an avalanche. On the other hand, if it is way too steep, if it is above 60 degrees, it is too steep that it cannot really hold a lot of snowfall. So there is a sweet spot between these two. Once again, what we do is we need to build a slope raster. For that, we use a slope raster function, and as an input, we provide the DEM data. On the slope data that we just got, we are going to reclassify that into the same 5 different zones. It's important to us that we keep the value of the different zones as the same, starting from 1 to 5. Then we again apply a color map. It could be the same exact colors or it can be different colors. It doesn't matter. Color map is only used for visualization. Once we apply different color ranges, we are able to see that on a map and find out the areas that have higher risk factors when we consider just the slope aspect. I shouldn't say slope aspect, because aspect is another factor that determines avalanche risk. So from past studies, people have found that when the slope faces the sun, such slopes will stabilize the snowpack much faster compared to the snowpack that is on a slope that is in a shadow. We are able to derive this kind of information when we produce an aspect data set out of the digital elevation model. And that's what we are building here. We use the aspect function to produce an aspect raster. Then we are able to reclassify the aspect raster into five different zones of susceptibility. Then we apply a color map, and we're able to look at it on the map here. So the slopes that are facing away from the sun, which have higher suitability for avalanches, are shown with red color over here. So we have looked at few different parameters that are derived from elevation. There is one more parameter, which is the curvature. So slopes that are convex in shape are considered more unstable compared to concave slopes, which are able to concave slopes, which are able to hold a large amount of snowpack. We are able to produce this curvature raster again from the elevation model using the curvature raster function. Once again, from literature, we know that certain values of this curvature is more suitable compared to others. So we're able to classify this curvature into the same 5 different zones of suitability. And we are applying a color map, and we're able to look at it on the map widget here. So we have looked at a few different parameters that are derived from elevation. Next, we are going to look at the land use land cover of the area of interest. We know that slopes or mountainous regions that have dense vegetation are less susceptible to avalanches compared to places with no vegetation at all. And also, places that already have snow or ice on them are also more susceptible to avalanches. So the first step is we clip the land cover data to our area of interest. Next, this land cover data is from the Esri Living Atlas dataset, and it has 16 different classes. We are going to reclassify this and pick the ones that are more suitable and give it a weight of number 5, and everything else is given ranges less than that. And we use the familiar remap function we have seen so far for doing this operation. Then we again apply a color map so we can look at it in a very more pronounced manner. So this is the land use land cover based suitability model. Then we have all our data set that we have collected so far. What we need to apply next is to multiply or assign a weight for each of these individual parameters. So we give a rather high weight to elevation, followed by different levels of weights for each of the different rasters. An important thing here is when you sum up all of these weights, they should sum up to 1, and that's what is happening here. It's very simple in the Python API to just multiply a weight with each of these raster. Each of these variables represent an imagery layer that we have been working with. Behind the scenes, what happens is each cell in the original raster is multiplied with the weight that you have applied, and finally it is all summed up together to produce a risk map. Then we apply a color map, and we are able to look at it here. This is just a preview, so we can put it on a map widget and see which areas have a higher avalanche risk. So the ones that have red color are identified as places that have higher risk of avalanches. So this was a very quick example to show how a suitability model can be built using raster algebra using the Python API. Next, we'll switch gears and look at an example of how to perform hydrological analysis using the Python API. And for that, I'm going to hand it off to Norman.
Hi. Okay, let's do some hydrologic analysis using ArcGIS API for Python. In this particular case, we're going to calculate height above near edge drainage, or commonly known as hand raster, for flood inundation mapping. To do this work, we need a digital elevation model where we will be using a 60-meter DM and channel head raster. Now let's see what is the workflow to do this job. It actually involves 4 main steps. First, we're going to hydrocondition the DM so that the water can flow correctly, and we're going to use fill function to do that. Then of course we need to understand where the water going, so we're going to do flow direction followed by flow accumulation and then the flow distance tool to create the hand raster. Let's take a closer look how we go about it. But we cannot really do any of this unless we can find our data on server, and to do that we have to connect to it. So we are going to import the GIS module from arcgis.gis, and then we're going to check the version first, because some of the hydrologic tools are available only version 1.3 or higher. So let's check our version. We're working with 1.7 version, so we're good. We can go ahead and do the work. Now I'm connecting to my portal so that I can get the data and eventually find the function that we need to do the job. Let's take a close look at the area that we're going to work with. And in order to do that, I am creating a map widget so that I can display the data. I'm now looking for my hug boundary so that I know the area that I'm working is the right area. So looking for the content, searching by name, and then getting the first portal item and the layer from it to show you. Once I display it in the map widget, I can actually see the area correctly. I can zoom in and zoom out if necessary, and look for the area. I can pan in this widget. So it's really very handy to see the data that you are working with in this map widget. Now that I have boundary, I'm going to look for the digital elevation model that I'm interested in. So searching the content and getting the DM that I need. Once I have the DM, I'm going to display it and make sure that is the DM I'm looking at. Getting the first layer from that portal item. Displaying it, and as you can see, it's actually showing high area and low area in this grid shading. The display is not great, but eventually we'll show you how can you make this display better. Now that you have this DM, you want to use it for the analysis, but you want to make sure that it's actually an image server. Image service. If it is not an image service, you cannot really use it for further analysis. So we're checking the type here, and then it is telling me that it's an image layer, so I'm good. I can go ahead and do my analysis. But as I said, my analysis also need the channel head, and what I'm doing now, I'm looking for the channel head. As soon as I find that channel head, I make sure that it is there, and I'm going to use it for further analysis. Now all the analytical tool is actually in ArcGIS Raster function, at least the one I need for now. So I'm importing all the functions so that I can use them one by one. The very first thing I want to do is I want to create a hydro condition DM by filling all the things. So obviously I am calling the fill function. Once I fill the DM, my next work is to calculate flow direction. And in this case, I'm actually using the D8 method and creating flow direction. The flow direction looks like this. It's very hard to kind of see what is going on because it's color coded. But if you actually look at the value, you will know that it actually computes the direction in which the water is flowing. Once I have the flow direction, the next thing is to calculate flow accumulation. It tells you how much water is flowing where. I'm using this flow accumulation function and using float option so that I can store large value there. After the flow accumulation is done, this is the time where we create our hand raster. Now as you can see, we are using a new tool called flow distance to calculate this hand raster, and this tool requires a couple of things as an input. It takes your flow accumulation, your DEM, and then the flow direction raster and compute the vertical distance, because that is what is the height above drainage. So we are doing the vertical computation for flow distance and creating it. Once I have it, I'm saving it, and then here it is. Now, of course, as I told you earlier, that looking at a data set in black and white is not always the best thing you could do. So what you can do now, you can actually use the color map method to display it in a different manner. In this particular case, we are using the elevation color map to display the information, and because the hand contained elevation or the height, you can use the elevation RAM to represent what is going on. And as you can see that some area you need much higher depth and some area has lower depth, and you can see it much clearly rather than a shade of black and white. So this is how you can not only perform a hydrologic analysis using ArcGIS Python API on Raster Analytics or ArcGIS Image server, and you can also display your result using a different color and nicely represent the output. Thank you.
We have come to the end of this talk. We showed you a few key examples of case studies in this talk, but a lot more is possible. I will request Norman to enlighten us about these different applications.
So why do we do raster analysis? So that we can create new data and information to make better decisions in many applications. Here are some examples. We can identify the area with risk of wildfire. And of course, when this kind of things happen, you want to look at what is the impact of that, the population that will be affected with this, and any other natural disaster for that matter. We can also manage watershed, cropping pattern, and farms, and actually make a better decisions about it. And we can also look at the changes that is happening over time with change detection or change analysis. We can also take a close look at our beautiful earth that we live on, right? And monitor the changes and the effect of our actions, such as loss of habitat, forest acidification, and the effect of climate change on human life that is happening as we are going into the new era.
Thanks, Norman. Let's do a quick recap of what we have seen so far. We learned that to perform raster analysis on the web, we use the raster module of the ArcGIS API for Python. We looked at the layout of this module and learned that it is composed of classes like the imagery layer, manager classes, raster, and a set of submodules that contain analysis functions. Through a Hello World example, we looked at the imagery layer and used its properties and methods to inspect important information such as different kinds of resolutions, etc. Then Norman walked us through the raster and spatial analysis concepts. We then learned about different types of operations and looked at an assortment of raster functions that are available, as you can see in the slide. We saw how functions are changed together and executed without producing intermediate results. Chunming then showed us how to use support vector machine classification algorithm to classify a satellite image of Iowa. She then showed us how to use the orthomapping module to produce digital elevation model and orthomosaics from drone imagery. Next, we switched gears and we saw an example of suitability analysis performed using weighted overlay technique. Then Norman showed us how to perform hydrological analysis. Thank you for attending this talk. If you want to learn more about the things that we discussed today, here are some links. The demos that we showed you are already available on the Python API doc site. And take a look at them over here. I provided the hyperlinks to those demonstrations. If you want to learn more about the theory behind spatial analysis and spatial stats, then check out these two books from the Esri Press. On behalf of my co-presenters and from myself, thank you for attending our talk. Bye.